Hello and welcome to this lecture on machine learning. Today we will be start with a simple computer science DBMS question, and then we will be solving an example problem on decision trees. Then we will be looking into SVM, support vector machines, and if we get time, we will be looking into the clustering algorithm as well. Okay, so fine. So we'll look at a very basic, simple question on DBMS. What is the as clause in SQL used for? Maybe take a minute or two and then let me know the answer. Yeah, something very simple. It is nothing but the rename operation. Okay, so we'll look into this data set. Okay, this data set consists of four features: outlook, temperature, humidity, and wind. And it's a historical data. So considering these features, whether the person played football or not, yes or no, that is our target variable. Okay, target variable is a binary classification problem. Whether the person played football or not, either yes or no. So it's a two-class problem, and we will try to draw the decision tree for this data set. So initially, on the top of the tree, which is the root, contains my entire data set D. So I can calculate the entropy of the dataset D minus summation, sorry, minus summation k equal to 1 to 2. Why 2? Because there are two classes, pk log pk, which is nothing but minus p1 log p1 minus p2 log p2. So what is p1? P1 is nothing but, if you look at all the data points, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 data points. Out of 14, let's say P1 denotes the probability of yes. It is 3, 4, 5, 6, 7, 8, 9. 9, there are 9 yeses. So 9 by 14 is a probability for P1. And for P2, it is 5 by 14. So this is nothing but negative of 9 by 14 log 9 by 14 minus 5 by 14 log 5 by 14. And if you calculate this, this will come out to be, just a minute, 0.94. Okay. So 0.94 is the entropy of our dataset D in the root case. Now, what we have to do is we have to consider each feature. So first, let us look at outlook. So now outlook is divided into three different values. One is if it is sunny. Another is if it is overcast or it is rain. So sunny, overcast, or it is rain. When it is sunny, there are two, three no's and two yeses. 3 no's and 2 yeses. If it is overcast, it is yes, 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 4 yeses. And if it is rainy, it is 1, 2, 3, 3 yeses and 2 no's. 3 yeses and 2 no's. I hope that is correct. 3 yeses and 2 no's. Correct. Okay, fine. Now, given this feature, if you see, if it is overcast, my model can claim that, conclude that with the data it is given, it can claim that, it can conclude that the um, output is that he will not play, he will play football. Yes. So now what I have to do is I have to calculate the entropy of D given outlook. This is nothing but you have to take a weighted average. The weight will be the weights of the individual features. So, which means how many values are there of sunny? So there are 3 different weights because 3 different class categories. 5 by 14 and entropy of D given sunny plus 4 by 14 entropy of D given uh, okay, just a minute guys. Yeah, D given overcast. So what we are trying to do is we are trying to find if outlook can be one of the features that can be used when trying to break our model, when trying to create our decision tree. Okay, so plus 5 by 14 entropy of the dataset D given it is rainy. Okay, fine. Now we have to calculate the entropy of each of these variables. So how do we do that? What we would do is the entropy of the dataset D given it is sunny is nothing but negative of summation k equal to 1 to 2 pk log pk. And over here, since I'm telling you that the outlook is sunny, right? You will only consider the data sets which are having the outlook sunny. Because if I'm telling you that the outlook is sunny, then I'm not considering any other data point, and then I'm only calculating the entropy based on this. And how do I calculate? Let's say P1 denotes the probability of yes. So out of these 5 data points, 2 are yeses, negative of 2 by 5 log 2 by 5 plus 3 by 5 log of 3 by 5, and then you will get some value. Similarly, the entropy of the data set D, given that it is overcast. Okay, I've exceeded annotations. I have to remove this thing. Okay. Given it is overcast is nothing but negative of P1 log P1. So let's say P1 denotes the probability of yeses. So now you look at all the data, all the points where it is overcast. This is one, this is another one, and they both are yeses. So it is 1 log 1 pk log pk minus 0 log 0. So log 0 is undefined, but what I can conclude from here is that the entropy of this case is 0. So if the entropy becomes 0, right, then I can claim that this is a pure leaf node because You do not have to break it any further. Okay. And similarly, you will calculate for E of D rain, given it is rainy. And then what you will get is the value of this one. If you do this average, you will get as 0.693. Now, what do I get from here? So now you will calculate the information gain on the given data set, considering I have considered outlook as a feature. Okay. Oh, somehow vanishing, whatever I write. Okay. Information gain on the data set, given it is outlook, is nothing but what is the entropy of the parent node minus what is the entropy of the child node. 0.63693. Okay. Let's write it as 0.69 only, which is 0.25. Right? Now, similarly, you will calculate the information gain for the other feature as well, temperature. Okay. So to calculate the entropy, let's calculate it for temperature also, just to get the clarity. So first I have to calculate the entropy of the dataset D, comma temperature, which would be a weighted average. So how many classes are there in temperature? Either it is hot, mild, or cool, right? Either it is hot, mild, or cool. And there are four hot, four cool, and rest mild. So 4 by 14 entropy of D, given it is hot, plus 4 by 14 again entropy of E of dataset D, given it is cold, plus 6 by 14 entropy E of dataset D, given it is mild. Okay. And so the entropy of the dataset D, given it is hot, is again minus pk log pk. So negative of, let's say P1 denotes the probability of yeses. So now you only look at the data points where it is hot, right? And then if you see, there are two yeses and two nos, right? That's the worst scenario anyone can have, but that is what it is. So minus 1 by 2 log 1 by 2 minus 1 by 2 log 1 by 2. Okay. Okay. Okay, sorry, it should be plus. Okay, sorry, that's the mistake I was doing. Summation, no, summation minus of pk log pk. Sorry, yeah, it should be summation. So this is nothing but minus of log 1 by 2, and if we consider log base 2, then this is nothing but 1. You can do the math, that is simple. I won't do this, but I think that's very straightforward, right? Log 1 by 2 is log 1 minus log 2. Log 1 is 0, minus of log 2 base 2 is 1. And 1 is the maximum entropy you can ever have on any data set. That's the worst case scenario. What is the entropy of D given it is cold? Is nothing but minus. So you only look at the points where it is cold. So you look at, cool, right? You see there are three yeses and one no. So 3 by 4 log 3 by 4 plus 1 by 4 log 1 by 4. Okay. And then this will be some value you will get. Okay. Not calculating. The entropy of the dataset D, given it is mild, is also negative of. Now again you go to the dataset, consider all the points where it is mild. 3, 4, 5, 6, 1, 2, 3, 4. 4 of them are yeses. So 4 by 6 log 4 by 6 plus 2 by 6 log 2 by 6, and then you will get some value. And then you again, the formula for information gain is the same. So information gain is nothing but what is the parent minus, if I write on the top, it somehow vanishes, 0.94 minus 0.911, which is 0.03. And similarly, you will calculate the information gain for the data set D for the feature humidity, and you will get 0.152. And similarly, the information gain of the data set D, given it is windy, is nothing but 0.048. After you get all this, what you have to select is, and also just for clarity, I will also write the information gain um, for the outlook variable. The information gain for the outlook variable was 0.693, 0.25, right? Now you select that feature which has the highest information gain, okay? Because 0.94 is the uncertainty when I consider the parent node. 0.911 is the uncertainty when I consider the feature, in this case temperature, okay? Similarly, 0.94 is a parent uncertainty, and if I consider humidity, it is 0.788. And similarly for windy, it is 0.8932. For outlook, it is the maximum 0.693, a minimum. So the information gain in information I get after I consider outlook is the maximum. Okay, the uncertainty will reduce the maximum. So that kind of says my first top of the tree is outlook. If it is overcast, I can declare yes. Okay, let me write this in green just for clarity. Okay. It could so happen that it is sunny. It could also happen that it is rainy. So if it is sunny, now your data set is 1, 2, 3, 4, 5. 5 data points are there divided across 3 no's and 2 yeses. So your data set has 3 no's and 2 yeses now. And if you consider rain, it is 5 data points again. This is yes, this is yes, this is yes. 3 yeses and 2 no's. Okay. Why did I say overcast yes? Because if you see overcast, there are only 2 data points. Sorry, there are 1, 2, 3, 4 data points. All are yeses. So my model can conclude that it is yes. Now, let's consider this node on the left. And I want to find what feature should I place here in order to break this further, because it is an impure node. This was nothing but 3 no's and 2 yeses. So what is the entropy of that node? Let's say this is D dash. This is D dash is nothing but minus of 2 by 5 log 2 by 5 plus 3 by 5 log 3 by 5, and then you will get some value, right? Minus 2 by 5 log by, which is 0.971. Okay. Now Now, if you see, I'm not calculating for all. I'm only calculating for the feature that I know is the best. For humidity, if I calculate the entropy, so now you are only constrained in the sunny data set. Okay, you're not looking at any other data set. And humidity has two values, normal and high. And high is 1, 2, 3, 3 high and 2 normal, right? 3 high and 2 normal. So I will do a weighted average 3 by 5. Entropy d dash given it is high plus 2 by 5 entropy of d dash given it is normal. Okay. Now my job is to calculate the individual entropies of these two. So the entropy of d dash given it is high is nothing but minus pk log pk. So p1 log p1. Okay, let me calculate p1 only directly. So p1 denotes the set where so you are only considering sunny and also considering high only. So in high there are all three are no's. So the entropy I can directly write it as 0. There is no uncertainty, right? It's always 0. And the entropy of d dash given it is normal is, you will calculate, look at all the sunny, you will look at all the data points where it is normal, which is this one and this one, and see they are both yeses, so it is also 0. In fact, this is 0. If it is 0, that means it's a very pure node, and I can say replace this d dash, right, with a decision node. Okay, decision node is just a term I said now. It's no, there's no specific term. What I wanted to say was I found the split. Okay, so this is nothing but your humidity. Okay, and humidity if it is high and if it is normal. So humidity if it is high, humidity if it is normal, it is yes. So humidity if it is normal, it is yes, and humidity if it is high, it is no. Okay, this is the tree that I made till now. Okay, similarly you will calculate for the other side as well, this side, and over here also you will have to find the adequate split. What you have to calculate, d double dash. Okay, so d double dash is a data set that contains 3 no's and 2 yeses, right? And this is a data set which has outlook as rain. So now your thing is only focused around outlook is rain. So this one, this one, this one, this one, and this one. Now, as always, what is the entropy of the parent node, which is d double dash minus 3 by 5 log 3 by 5 minus 2 by 5 log 2 by 5, which is nothing but 0.971. Now what I will do is, I will also calculate this one for uh, the thing that I know. Okay, I have an oracle which tells me what is the correct value, which feature is there. So that's why I'm not wasting time that much here. So I know for wind, it is the best, and wind is also a two class feature, two category feature, either strong or weak. So entropy of d double dash given the wind is nothing but you will take a weighted average of, you are in rain, so there are 1, 2, 3, 3 weaks and 2 strongs. So 3 by 5 entropy of d double dash given it is weak plus 2 by 5 entropy E of the data set d double dash given it is strong. Okay. Now the thing is to calculate for E d double dash given it is weak is nothing but look at the weak data sets 1, 2, 3 and you see all are yeses. So the entropy is 0 and the entropy of d double dash given it is strong is nothing but 1, 2 and both are lows. So it is also 0. So this is the weighted average is also 0. Okay. So your tree was previously like this outlook. Okay. If it is overcast, you had a decision. If it is windy, you will have a decision. And if it is rainy, I looked at humidity, which had, so this is a feature, which had two values, either high or it is normal. Similarly, wind, either it is strong or it is weak. So if it is strong, then technically you should not play. That is what the data set also says. So if it is weak, it is yes. If humidity was normal, it was yes. And also if it is overcast, it was yes. And if the wind is strong, you won't play. If the humidity is high, you won't play. So given any new data point you have, you will just uh, go to the root of the tree, look at the valuable outlook. If it is rainy, you go to the left. If it is overcast, you output yes. If it is wind, if it is, oh, okay. So, okay. I think I did some small error. Sunny and rain. Okay. So this was sunny and this was the rain. So if it is sunny, then you will look at the humidity value. If the humidity is high, then you output no. If the humidity is normal, you output yes. If it is overcast, you output yes. If it is rainy, then you look at the wind variable, look at the wind feature. If it is strong, you will output no. If it is weak, you will output yes. This algorithm that I used was using the entropy, right? And this usage of entropy, this uses entropy and information gain. And that is why what I can say is this one as this algorithm is called the ID3 algorithm, iterative dichotomizer algorithm. It uses entropy. There is one more algorithm called CART, classification and regression trees. The only difference between these two algorithms is the CART tree uses the Gini index or Gini impurity as the impurity function rather than the entropy. Okay. Okay. Fine. Okay. Maybe I will let you settle in for a while. Think through, look at the solution. If you have any questions, feel free to ask. Give you 2 minutes to think. Just beat your head around. We'll now start with clustering. Hopefully, we'll be done in an hour by 11:30, and then we will actually go with the clustering algorithm. Okay, it should not take more than an hour, but let's see. Okay, fine. Just think about it for some time. Think about the solution we just designed, the tree we designed. And let me know if you have any questions. Technically, what you should do is, once you are in any parent node, let's say you are here, then I knew that wind was a feature to break it through, but typically computers, what they do is they try to calculate the entropy given each feature. Okay, so you have already considered outlook, so you won't consider that again. In this point, you will consider humidity. You will consider other features as well, which are there. One of them, temperature, and consider that as well. And then maybe whichever gives the maximum information gain, we'll select that as a feature to uh, build your tree. So think about this, and we'll meet in some time, 2 minutes. 10:35, we will start SVM. Okay. Okay, no questions. Fine. So let's come back to a model that we learned earlier called perceptron. My YI was, let's say, a binary classification problem having two labels -1 and +1. And my assumption is still the same, that the data is linearly separable. So let me give you an example of a perceptron model and where it might fail. Let's say your perceptron model find out a hyperplane like this. Let's say this is the hyperplane that your perceptron found. It separates out the negative classes and the positive classes perfectly, the green class and the red class in this example. But if let's say I had a test point over here, okay, what label do you think should have been assigned? It might seem that by the assumption, by that, this is rather a red point rather than a green point. But my perceptron will classify it as a green point, correct? Because it falls in the green region. What I can do in this scenario is I can find another line that separates out the margins very perfectly, which means let's take this line. Now the margin is the maximum. Hope you know the margin. Margin is the minimum distance of the point, a point which has minimum distance from the hyperplane. So the margin, if I consider the maximum, then that is called maximum margin classifier, and that is also called the support vector machines. Now, what is the meaning of support in the support vector machine? If you consider this as a support vector, this as a hyperplane, then the line that is passing through the point X in this scenario, and in this scenario, this one, these two are called the support vectors, and that's why it's called a support vector machine. The hyperplane that is drawn is supported by the support vectors on the edges. So what the SVM tries to do is it tries to find this max margin classifier. It tries to find this maximum margin classifier. And thereby the margin, right, H, nothing but whatever point falls on the hyperplane, the equation of it is W transpose XB, X plus B is equal to 0. Pictorially, let's take as this hyperplane, and let's take this as a vector W. This is the vector W, and this is the hyperplane. Let's consider any point X over here. Okay. Now let's project this point x on the hyperplane. Let's call it xp, the point projected on the hyperplane. And d denotes the vector, that is this vector, the projection vector. Okay. Now, according to the vector law, xp is nothing but vector addition is x minus t. So typically we would draw this as a, so this is my vector x, right? And by the vector addition rule, x is nothing but xp plus d. So x is nothing but go xp and then d. But rather, here it is. So let me write d here so that you don't get confused. So x is nothing but xp plus d. So xp is x minus d. Now, since we know that xp lies on the hyperplane, because xp is nothing but the point projection on the hyperplane, projection of point x on the hyperplane, I can say that W transpose xp plus b is equal to 0. I just plug it in the equation of the hyperplane, the point xp. And now I can substitute the value of xp here. So W transpose x minus d plus b is equal to 0. Okay, I'm exceeding annotations again. Equal to 0. And then also one more thing that you can understand here is that my vector d here, since W is perpendicular to the hyperplane, D is also the perpendicular to the hyperplane. D and W are parallel. Right? My D and W are, so this is my W. Now D is parallel to W. So I can also say that my D is nothing but some alpha times W. W is a unit vector I consider, let's say. So D, can I say, is some alpha times the unit vector W. Okay. So I can substitute the value of D in the equation given earlier and say W transpose X minus D, which is alpha times W plus B, is equal to 0. Okay. And if I know the value of W, I know X, I know B, I just need to find the value of alpha. And if I want to solve this equation for alpha, alpha is nothing but W transpose X plus B divided by W transpose W. Okay. And if I find the value of alpha, I can substitute it in the equation for D and say D is W transpose X plus B divided by W transpose W vector W. And the length of D, which is the norm of D, is nothing but L2 norm of D is D transpose D, which is nothing but root over alpha square W transpose W. I can pull the alpha out, alpha root over W transpose W. Now in this equation, I can substitute the value of alpha and say that the L2 norm of D is nothing but W transpose X by W transpose W and root over W transpose W. So I can write this as divided by root over W transpose W. Now this thing is a very common result in geometry, which is a distance of a point X from the hyperplane. From the hyperplane. Okay. Now we would want to margin denotes the minimum distance. Okay. So the margin gamma given W and B will be nothing but for which value of minimum X my W transpose X plus B by L2 norm of W is the minimum. That is my margin. Okay. That is the definition of margin as it is. So the goal of support vector machine will be to find a W that maximizes the margin. So what do I mean by maximizes the margin? I would want to find a vector hyperplane W. In this scenario, the line that I drew, which is this line, can't because okay, this line W that maximizes this margin. So in essence, what I want to do is I want to find the maximum value of W comma B, maximum value of the margin gamma W comma B, the corresponding values of W and B. And the constraint that I have here, so if I just say that I want to calculate this, which is the maximum margin of my W that has the maximum margin, then if I have a data set, let's say this one, let's say some data set, okay, this could be my margin. This could be my W, which is the margin that it has a maximum margin, right? So what is the problem here? We have to also consider a constraint that they should also be able to classify the variable, classify the points correctly. So the constraint is that yi times W transpose xi plus B should be greater than or equal to 0 for all I. Okay, fine. So if I substitute the value of the margin minimum of X belongs to the data set by W transpose W. Okay. Now this might seem a bit daunting that why the heck I have something maximum, something also minimum. Okay, so which is something that is not very counterintuitive, but I will again explain why this is the case. Okay, so what I will do here is I will apply a trick. So max W comma B, I can pull out the constant out. So this is nothing but 1 by W transpose W, right? Minimum of X belongs to the data set. W transpose X plus B is equal to 0. And what I will do here is I will apply a trick called rescaling, which means I will say that my minimum of X belongs to the data set D is nothing but W transpose X plus B equal to 1. Now you might be thinking, why the heck can I do this? Okay. See, W transpose X plus B is just a value. Okay. Let's say the value is 1000. That's the minimum value, let's say. I can just divide it by 1000 and say it is 1. Or let's say you tell me that the value is 5. That's a minimum. You can divide it by 5 and claim that it is 1. So what I'm doing is I'm rescaling. So if I do this, now my thing becomes very, very simple. In the sense, I just have to maximize my W comma B 1 by W transpose W. Because my min of X belongs to D, W transpose X plus B is 1. And maximizing 1 by X is nothing but minimizing X, right? So this is but minimizing W transpose W. And the constraint is updated now in the sense my yi times W transpose xi plus b should be greater than or equal to 1 in this case for all I rather than 0. And why so? Because my minimum value of x belongs to t is 1, right? And so yi times that should be at least more than equal to 1. I just combined the two constraints that I gave earlier. One constraint being yi w transpose xi plus b should be greater than or equal to 0. Another constraint being w transpose x plus b, the mod should be equal to 1. So this is nothing but the optimization problem with a given constraint. Okay. So let me write in a different color. You have to calculate the minimum value of w comma b w transpose w such that for all data points I belonging to the data set, my yi times w transpose xi plus b is greater than or equal to 1. Okay. Okay. So what I will do now is, this is the final SVM problem formulation that we have done. But SVM has some more cool features compared to a perceptron. If you remember, in a perceptron model, if your data was not linearly separable, let's say there is only one point which is off, for which your data becomes not linearly separable. Right? In that scenario, perceptron will just loop forever. It will not give you a model. It won't even give you an approximation. It will just spit out any bullshit. Okay? It will just keep on looping forever, trying to converge, and it will never converge. It will go into a infinite loop. Okay. So there was a there was a yeah, okay, sorry. So there was a formulation of something called a slack variable. Okay. Now what does the slack variable do is, you we try to relax some of those points in the sense W transpose W such that for all I, yi times W transpose xi plus b should be greater than or equal to 1 minus sigma. Some very small variable sigma I, where for all I the value of sigma I is greater than or equal to 0. Okay, this is called a soft margin classifier. Now, what this means is whenever your model, you're not exactly finding the margin as 1, you're not actually able to find the minimum value of x belongs to D in the data set W transpose x plus B as 1. It is some value 1 minus some small value psi I, which means if you consider any simple data set, yeah, sorry for the noise, I think there was some noise. So if you consider small data set of crosses and circles, okay, let's say there is one point that is here. So your minimum distance is actually not 1, it is 1 minus that psi I. Okay. So to account for these small variations, we try to use the slack variable. And over this, we consider this type of classifier as a soft margin classifier. Okay. So, and I will only consider the psi I, this sigma I, sorry, we call it psi I, the slack variable. We only consider psi I when there is an incorrect classification. We do not consider it when there is a correct classification. What do I mean by this is, okay, we are going to clustering not now. So what do I mean by this is, this psi I is nothing but 0 when yi times W transpose xi plus b is greater than or equal to 0, or else it is 1 minus yi W transpose xi plus b when it is less than 0. Oh, sorry. It's less than 1, greater than or equal to 1. If it is greater than or if it is less than 1, that means my yi times W transpose xi plus b is either incorrectly classified, or if it belongs to the hyperplane, it belongs in that region, in this shaded region, right? So in that scenario, I will consider the slack variable. And my objective in this sense, I will write it, okay, maybe I'll take this one, that's fine. I will take this as SVM only. Is nothing but my objective is now changed to minimum of W comma B W transpose W plus C times psi. Okay, which is also nothing but W transpose W plus C times max of 1 minus yi W transpose xi plus b comma 0. So I just try to write these two equations as a max function, and this is my L2 regularization. If you remember L2 norm, while this thing here is very popularly called the hinge loss. the hinge loss. Okay, so this was SVM. Me talking about SVM and why we use SVM and how to formulate SVM and how SVM works. It tries to find the maximum margin classifier. So I will give you guys a 2 minute break. Beat your head around SVM, what you learned now. Just settle down for some time learning about SVM. So it's not easy, I understand. You won't get it in the first go. You will have to repeatedly look into it. So that's okay. I hope you will be able to do that. And we'll meet in some 11:05. It's 11:02 now. And then we'll discuss on clustering algorithm, starting with k-means clustering. Okay? Thank Okay, so let's start with k-means clustering. It's a clustering algorithm, which is an unsupervised learning algorithm. And if you don't recall, then unsupervised learning algorithm is an algorithm where you do not have access to your class target variable. Okay, You do not know the target variable, you just have the data sets, and then you try to find out some patterns, discover patterns in the given data sets. So this doesn't always work, I guess. Okay. 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 Sometimes it doesn't give feedback, but it still works. Okay. Crazy. Let's say there are two features. Let me pull this on the side a bit. I can utilize the space on the right. Okay. Let's say this is a bit to the here, this is a bit to the here. Okay. Okay. This is not straight. Okay. Okay. Fine. So let's say that there are two features, F1 and F2, and since I don't know the class label, so I will only draw this as crosses. So let's say these are some data points. Okay. A typical clustering algorithm will cluster these points into one cluster and these points as another cluster, right? So the k in the k means denotes the number of centroids. So the k in the k means clustering is one of the ways to find out such clusters, and k denotes the number of centroids. Okay, and the algorithm is very simple. So what is a centroid? Let's take this cluster. This cluster has a centroid here. Let's call it C1. This cluster here has a centroid called C2. Right? The steps to perform to run the k-means clustering is something very simple. So very easy algorithm, guys. Steps to perform. Number one is to try different values of k. Okay. The second step is to randomly initialize the cluster centroids. The third step is to, using any distance metric you want, let's say Euclidean distance, compute the Euclidean distance between all the points and the centroids. So let's run it on this data set. What I mean is, you initialize two centroids. So let's say this is one centroid C1, this is another centroid C2. Okay. Then what you would do is, you compute the Euclidean distance between all the points at the centroids. So you consider C1, take the Euclidean distance with all the points. Consider C2, take the Euclidean distance with all the points. Whichever point lies near to whichever centroid, you label them as a cluster. In the sense, see, This point, this point, this point, this point, this point, maybe this point, all lie to C1. Okay. Maybe, and this point, maybe this point also lies to C1. This point, this point, this point, this point, this point, this one, this one, this one, this one, all lie to C2. Okay. Okay. That's how you find out. The fourth step is to update the centroids. So the fourth step is update the centroid. How? So Ci prime is nothing but 1 by how many points are there in the cluster Ci and of Ci. Take an average of all points belonging to Ci, and that will be your new cluster centroid. And you keep on running this algorithm till the point where you find that the set of points in each cluster is not changing. And that's when you terminate your algorithm saying you have found the perfect set of clusters. Now, one thing you might be wondering is how do I actually decide the value of k? Looking at the data set, we can say it is 2 or 3, but how will the computer understand? So what I do is I, I use something called the elbow method. Which is something very simple. What I do is, if you consider any data set, let's take a simple data set. Okay. Okay, some simple data set we are considering. We will run an algorithm for I equal to 1 to 6. Okay. We will consider the value of k as I. So initially we'll consider 1 point, next we'll consider 1 cluster, 2 cluster, 3 and so on. And then we will consider computing the error, which is nothing but WCSS for that given k, which means within cluster sum of squares. So what does it mean? If you, let's say, consider k as 1, so this is your centroid, you calculate the distance between all the points in the centroid, and the sum of squares, the sum of squares of the distances from the centroid of all points is the within cluster sum of squares distance. So the WCSS is nothing but you would look at each cluster from 1 to k, you would look at each point x belonging to that cluster C and sum over x minus the centroid of that particular cluster C squared. This is the within cluster sum of squares distance. And if you plot it as a graph across different values of k, you will get a elbow curve. And this way you can decide which one gives you the, let's say this one or this one, which one gives you the optimum value of k for which you can find out the that will be your value of k. This is other than this is also can say this as a brute force method. Now, a small variation happened to the k-means clustering algorithm, and they called it k-midoid clustering algorithm. It's very, very simple again. So what I will do is I will draw a data set of two features f1 and f2. Okay, and these are the point 2, 5, 8, 3, 7, 6, 1, 4, 9, 5, and f2 is 3, 7, 3, 5, 2, 8, 4, 6, 5, 4, 8, 4, 654. Might not have said someone's number, but okay, fine. 846543735 Okay. These are 10 data points of two feature values f1 and f2. Okay. We want to again fit the uh, we want to define the clusters. Okay. So very subtle difference. The first step remains the same, which is to select a value of k. Okay. And here they are calling k as the number of medoids. Now, what is medoid? Again, don't worry, I will explain. The second thing is, okay, second thing is select two medoids. So medoids can be from the data set. Let's say this is the first data set and the second data set. So just randomly you will select two data points. Let's say D1, D2. The second step is you initialize. Okay. So previously you initialize randomly. Here you initialize using the data set. The second step is to calculate, instead of the Euclidean distance, you calculate the Manhattan distance. That is the main difference. Manhattan distance of every point to the medoids. And then you will cluster those points depending on the Manhattan distance. Whichever is smaller goes to one cluster. Which points are smaller than that. Okay. And then you update your medoid. Similarly, similar case, you calculate the within cluster sum of squares and update your medoid. So the only difference was to how you are initializing the cluster algorithm, which is you are considering two data points D1, D2. And then you are also looking at calculating the Manhattan distance, which is f1 minus f. Okay. So let's say there are 2 points x1, x2, x1, y1, and x2, y2. The Manhattan distance is nothing but x1 minus x2 plus y1 minus y2. Okay, there's nothing but the we have seen earlier as well, right? Absolute value of x1 minus x2 and y1 minus y2. Okay, right. So very small variation, nothing much here. Okay, now okay, so I did not wanted to end here. There is one more small algorithm that we will discuss today called hierarchical clustering. Okay. But if any of you have any questions, feel free. Wait for 5 minutes. We have been doing a good sense of algorithms today. We learned three algorithms today, so that's a feat in itself. So maybe just um, take some time. We'll meet in 5 minutes. Okay, I'll give you a 5 minute break, and then we will discuss the last algorithm, hierarchical clustering, and then I will leave you for the day. And if you have any questions, feel free to ask. Okay, welcome back. No questions. Okay, fine. So now let's take a simple data set, and this is the last algorithm we will discuss today, which is hierarchical clustering. Let's say there are two data points here. Let's say there are two data points here. Let's say there are three data points here. So what I do is, the first step that you have to do is, I have to draw something called a dendrogram. Okay, doesn't work always, so I have to draw by hand only. To draw something called a dendrogram. Okay, so it has, I'll just name it. So the y-axis denote the distance. Okay, this denotes the distance, and the x-axis denotes your points. So each of these points I will label p1, p2, p3, p4, p5, p6, and p7. So p1, p2, p3, p4, p5, p6, p7. So p1, p2, p3, p4, p5, p6, p7. First step is to compute the distance of each point with every other point. Okay. Consider P1, consider the distance from P1 with every other point. P2, consider with every other point. Similarly, P3, P4, P5, P6, and P7. And the first step is to find out the smallest set of two clusters, which means two element clusters. And if you see, this is one, and I will draw the corresponding bar of the dendrogram, which means P1, P2 are joined to each other. Also, if you see, P6 and P7 are also can be a two element cluster. So I will join, and this might be having a distance 2 because I will. So the algorithm works out, you will consider the shortest distance first between 2 points, which is P1, P2 in this case, then the next shortest, and so on. And then you will also might consider this also as a next possible cluster. Okay, this was the first iteration. In the second iteration, you will try to include some more points. In the sense, what you will do is you will try to see that if I consider P4 as well in this cluster, then this can be a three element cluster. So I can say this is nothing but P4 goes to the top, right? And then I join it with, okay, doesn't go all the way, it goes till 4, let's say, and then it comes down here. And the next step that I can do here is I can consider the next set of clusters, which is I can join P1, P2 with the entire cluster, blue cluster. So this one can be my next cluster. Okay. So what happens here is I can consider P1, P2, and join it with this cluster, and finally I can consider P6, P7 along with this one as the final cluster. Okay, this is my dendrogram. So this diagram is called dendrogram. So did I make any assumptions on the number of clusters or anything? No. That's the advantage of this algorithm. Now, how would you find the clusters? So to find the clusters, okay, what you will have to do is you will have to find the longest vertical line You will have to find the longest vertical line that has no horizontal line passing through it. Okay. What do I mean by this is, if you consider this line, then there is a horizontal line passing through it. You can't consider this line, horizontal line passing through it. If you consider this line, see, this line can be considered as one of the possible candidates of the cluster. And typically you can extend this horizontal lines all the way around. So this is nothing but something like this. And wherever it intersects, okay, these are actually your clusters. Okay. In this case, it has 5 different clusters. So this is the hierarchical clustering algorithm. The final topic that I would want to discuss is to how do you validate a cluster? Whether the clustering algorithm was able to cluster the points properly, or it was able to do it properly or not. How do you validate the cluster? We compute something called a Silhouette score. Again, I'm sure there won't be any question which asks you to uh, compute the Silhouette score, because it is not very, um, it takes a lot of time to compute it, but still, for theoretical purpose, you should know Silhouette score. Hey, come on, it's always going away. Okay. Okay, let me write it here then. Yeah, Silhouette score. Okay, what is Silhouette score is, once you have found any cluster, once you have found a cluster, let's say this is a cluster of data points. Okay, it has a given centroid, and these are the points on the cluster. Okay, you calculate two variables. One is AI for a given data, any data point I. What is AI is 1 by the number of clusters, number of points in that cluster. So let's say this is xi. So you want to calculate for this one. Let's say this is xi. You want to calculate the Silhouette score for xi, this point. Then you will consider all the points in its cluster, which is c sub I minus 1. By minus 1, I will explain. And you will calculate the distance of all the points belonging to that cluster, where I is not equal to j, distance of that point xi with xj. So you calculate the distance of xi with each one of the other points. Okay. Okay. And you are not considering the ith point, so you are considering one less point. So that's why it is ci minus 1. This is the average distance within a cluster. Within a cluster. Okay. And similarly, you will also compute something called, for the given point, you will also consider something called d of I. Okay. Which is nothing but, you will now consider another cluster. Let's say this is another cluster. So, and I'll just write the formula down. Minimum j is not equal to I. So you are not considering the same cluster. The average distance of the points in the cluster from. So if you, let's say, have some clusters around I, so this is my ith cluster, right? This is my ith cluster. You will consider the cluster that is nearest to it. It could be this one. Let's say it's this one. So this is my cluster J. Okay. And then you will compute the distance of xi with all the points in cluster J. Okay. So AI denotes the within cluster distance of a point xi, and bi denotes the distance of the cluster with the nearest cluster. And for a good clustering algorithm, you would typically want BI to be much more than AI, right? Because you would want the separation between the clusters to be the maximum. So the Silhouette score SI, just this metric which says compute the difference between BI and AI divided by normalize between the maximum of AI comma BI. So this kind of says that my SI could lie between -1 to 1. So if the value is 1, which means my BI is much greater than AI, that is the best part. And if it is less than 1, if it is less than 0, or less than 1, more it is closer to 1, the better the cluster you have. More it is closer to -1, the worse the cluster you have. So if it could be negative only when the value of AI is more than BI, which is, so it's not very easy. Okay. So it's very intuitive. So if the value of BI is more than AI, then your Silhouette score will be greater than 1. It will be greater than 0. So your difference is not negative, it's positive. And if it is AI is greater than BI, then the difference is negative and you will go. So more you are going to 1, better the algorithm, more you are going to -1, the worse your clustering. Okay. So this was clustering. Another quick glance at the syllabus, what we have covered today, what we will cover in the next class. We have covered SVMs. We have covered clustering algorithms, k-means, k-meter, trajectory, everything. We are only left with single linkage and multiple linkage and top-down agglomerative clustering algorithms, these are called. So agglomerative clustering is left and feed-forward neural network. So maximum 2 classes, even let's see, one class is not, let's say if I do it in one class, but not possible, I guess, because feed-forward needs another class in itself. This is very simple, the agglomerative clustering, but maybe I'll dedicate 2 classes for it. And next class, we will look at feed-forward neural network. And after that, we'll look into single linkage, multiple linkage, and also we'll solve some problems. Okay, so let me stop the recording. Before that, anyone has any questions? I'll wait for some time for any questions. Okay, anyone has any questions? Okay, no problem. I'll send the lectures on the chat. Yeah. Okay, I'll stop the recording. If you guys don't have any